if I go back to the pre-analysis framework that we saw before while discussing what's under the black box, the first thing we need to think about is what is the mathematical model to be solved. And then we'll talk about how to solve that mathematical model using the finite element method. And the mathematical model consists of governing equation, which is a differential equation, and boundary conditions. Let me talk about the governing equation. Going back to my graphic of the example problem, this indicates a tiny volume within the element, a vanishingly small volume within the element, okay? It's called a control volume, and in my next slide, I consider this volume. And let's say, the dimensions are delta x, delta y, delta z, this being the x direction, this would be y and this would be z. And I look in the limit as these are almost zero, okay? These tend to zero. And that's why you say it's an infinitesimal control volume. Now they're almost zero, but they're not zero, because the whole framework falls apart if they become zero. That's a trick in calculus. It's almost zero, but not zero. And it took me, several years to figure out that that's a trick it's playing. And then let's do an energy conservation for this infinitesimal control volume. Let me consider this phase here. And there is a heat flow through that phase, which I will denote as Q sub x. And then there's a heat flow, actually this is a heat flow in, and then there is a heat flow out through that phase, which I will denote as Qx plus, so it's going to be, it's going to be slightly different from that because, that distance is vanishingly small. And that change I can find from the gradient. So if the rate of change of Q sub x is that, if I multiply it by the distance, I'll get how much it's changed. Okay, and so that's a small difference. And you're going to get higher order terms, that are going to be proportional to delta x squared, delta x cubed, and so on. But in the limit, as delta x tends to 0, I can ignore that. So that's why this is, this is important, because I can ignore the higher order terms. Okay, so the heat flowing out is slightly different from the heat coming in. And I can write the net heat flow out is going to be, okay, this is going to cancel that, so it's going to be just the change from this phase to that phase. That's given by this term here, okay, so that's that term. And now I can relate that to the temperature using Fourier's law. And many of you should have seen this before. It's like the foundation of heat conduction, which says that, the heat flow is proportional to the temperature gradient. Okay, so if the temperature gradient was larger here, you'd get more heat flow. If there was no change in temperature near that phase, then there would be no heat flow through that phase. I think that's intuitive. And there's a constant of proportionality, which is K, and I get a negative sign. And the negative sign you need because temperature, the heat flows from higher temperature, lower temperature. That is in the direction of the decreasing temperature. That's what that negative sign indicates. K is called thermal conductivity, and we'll assume that it's a constant. Okay, and this term gives me per unit area. So I need to multiply it by the area of the phase, which is going to be delta y delta z. Okay, so that's that area, and I'll get the net heat flow through any phase. So now if I substitute that back in here, okay, I'll get the net heat flow out in terms of the the temperature. But one thing to note is, when I substitute it back, I have to differentiate this. So what will happen is I'm going to get a second derivative of the temperature. So let me do that. I'll get a term. So the purpose is not to derive this rigorously, but to do it intuitively so that you get a sense of what the physical significance of each term in the equation means. So you're going to get a term that looks like minus k d squared t dx squared, and then you have delta x from here and delta y and delta z from there. Okay, that's so this represents a net heat flow through the faces, and I'm going to be assuming 1D. So let me list assumptions here as I'm going along. So I have assumed one-dimensional. So I'm going, I don't need to. I'm saying that there is no heat flow through these faces, or through this, this face. One-dimensional or 1D. I also have assumed that there is no variation of the temperature with time. So I'm assuming that it's steady, and I'll also assume that K is a constant. That is, we have constant thermal conductivity. We can relax all these assumptions, but just make the details more complicated. And I also say that there is another term contributing to the heat, which is the heat generation. So I have some heat generation per unit volume, which I call Q. And so the net heat out, and Q, this is per unit volume. So the net heat out is going to be what's flowing out minus what I'm adding through heat generation. So that's going to be minus Q, and that's going to be proportional to the volume. Okay, that's per unit volume. So that's going to be delta X, delta Y, delta Z. Now one thing, one key thing to keep in mind is this term, or this term, accounts for what's coming in through the faces. This term, which I'll add here in a moment, accounts for what's coming into the volume. Okay, so they're different that way. One is related to the surface area, the other is related to the volume. And if I bring that in here, I'll get minus Q, delta X, delta Y, delta Z. And if energy is conserved, and I have no other effects, the heat going out plus minus the heat added should be equal to 0. And I can divide through by delta X, delta Y, delta Z, and I'll get my final governing equation, which will look like K d squared t dx squared plus Q is equal to 0. Okay, that's called the heat equation, and that represents energy conservation for an infinitesimal control volume. That's a governing equation. We need to, and this is going to be defined over the length of the bar, and we need to add in the boundary conditions, which I'll do when I summarize the mathematical model.